So, okay, folks, we are going to sort of pick up where we left off in the last class. And if you'll recall, the last topic we were talking about, what was it? Hopfield networks. It's there on the slide, right? So, and what was the last topic we covered on Hopfield networks? Anyone recall? How many patterns you can remember, and how you can train a Hopfield network to remember patterns. We were looking at the Hebbian learning framework. So let's do a quick recap of everything we've covered. Here is our definition of a Hopfield network. It's a symmetric. It's a loopy network with symmetric connections. Each neuron in our case is a perceptron with a binary plus minus 1 output. And so the way it worked was that at each time a neuron receives a field which is the sum of the signals from every other neuron, and if the sign of this field matched the output of the neuron, that is, if the sign of the field was positive and the output of the neuron was also positive, or vice versa, the neuron wouldn't respond. On the other hand, if the two signs were mismatched, the neuron would flip. Basically, the neuron is always trying to align itself with the sign of the incoming field. So we saw that when we have a network of this kind, the neurons begin flipping, and the network continues to evolve. It doesn't evolve ad inf. You can define an energy for the neuron, which is for the network, which is a weighted sum of all pairs of outputs, and the weights here are just the weights of these edges. The network will continue to evolve until this weighted sum arrives at some local minimum. We saw that every single evolution must reduce this energy. Now, in vector form, we also saw that we could write this energy out in this manner, which is this quadratic. Basically, this is if you actually expand this out, W times Y is going to give you a weighted combination of all of the neuron outputs, and then Y transpose W times Y is just basically going to give you this term summed over all pairs, and so there's a minus half to make sure that you're not double summing, right? So this is simply the linear algebraic form of writing exactly this energy term, and the network will continue to evolve, and each evolution is going to reduce this weight, this energy. So you can define an energy contour, which is the value of this energy term for different network configurations, different patterns at the outputs of the neurons. And if the network is initialized at some pattern, the bits will begin to flip until the network arrives at some local minimum in the energy. This, we saw, is content addressable memory. If you could somehow design the network such that these patterns, these local minima, were patterns that you wanted the network to somehow remember, then if you initialize the network at some corrupted version of these patterns, the network would self-correct these patterns until it recalled the entire pattern. So this was content addressable memory, where you have multiple values stored in it, and the network, you can recall any particular value by initializing the network with something that is close to it, or some corrupted version of it. So we also call this associative memory, in that every noisy pattern has some associated stored pattern, and it's going to pull up the pattern that's most associated with the current pattern stored in the network. So this entire process was analogous to spin glasses. We also saw this in the last class. A spin glass is basically a dielectric medium with lots of dipoles in it, magnetic dipoles in it. Each dipole is going to align itself to the local field And in doing so, the dipole may flip to align itself. And if the dipole flips, it's going to change the field elsewhere. So this may cause other dipoles to flip. And that may in turn change the field at the current dipole, which may be caused to flip, and so on. And so once again, in this physical system, we saw that you could define a field at each dipole, which is a weighted combination of all the other magnetic dipoles plus an external bias. So this is a magnetic field at each dipole. And the dipole is going to try to align itself with the sign of the current field. So in this case, we saw you could define a total energy of the system. There's a reason we're going to be talking about the energy of the system, as you'll see, and towards the end of this lecture, where the total energy of the contribution to the energy of any single dipole is the product of that dipole with the local field. And so over the entire medium, the energy is simply the sum, the negative of the sum over all pairs of dipoles of the products of the weighted sum of the products of the dipoles, where this weight jij depends on the medium, the distance between the dipoles, and other factors, plus an extra term, which is the contribution of an external field, right? So once again, this kind of system would evolve as time. If you initialized it at some value, the dipoles would begin to flip, each dipole trying to align itself with the local field until it arrives at some local minimum and the energy. So the system remembers its stable state and returns to it whenever possible. This kind of behavior is in fact the basis of some of these materials which shape memory alloys and things like that, which remember their own shape. So a phenomenon very similar to this is what is used even in those things. So in the computational equivalent, which was the Hopfield network, the way the Hopfield network would operate was that you'd initialize the network somehow, and then you'd loop through all of the neurons and set each neuron to align itself with the field at that neuron. And you'd keep looping through this until this iteration converged. The updates could be done sequentially or all at once, and convergence happens when this energy doesn't change significantly anymore. So one thing that that you might want to remember is that if I have the network, I can write the patterns, the outputs of each of the neurons as a vector. And the way the network is evolving is just taking the sign of W11, W12, W1n, Wn1, Wnn, Y1, Y2. So this is how the network evolves. I can write the whole thing in vector form, and I can write this as y equals sine of W times y. So basically, we're going to keep referring to that particular equation a few times. Each neuron is each row over here. The diagonal terms are all self-weights. They're typically 0. Each row over here multiplies this current state of the neurons and gives you the field at the current neuron. And the neuron tries to align itself with the sign of the current field. So the entire thing can be written in matrix form like so. Questions? It's very straightforward, right? So we saw some examples of content addressable memory where we had networks designed to remember different kinds of patterns. And if you just gave it partial, corrupted or partial versions of these patterns, it would recall the entire pattern. So when you train these networks, the point was how to make the network store specific patterns or specific sets of patterns. And here there are a bunch of different approaches. The one that we saw was Hebbian learning. But then when you also train this network, a second question that arises, how many patterns can we actually store? We saw the simplest form of training, which was Hebbian learning. If you wanted to store any particular pattern, then you just, a single pattern, then you set the weight to simply be the product, the weight between any two neurons to be the product of the values you wanted those two neurons to have when the network evolved to a stable point. So everybody recall this one. And we showed that this is both stable and stationary if you're storing only one pattern. And I can actually write this thing like so. When I say Wij equals Yi, Yj, if I represent Y as Y1 through Yn, then Yi, Y transpose is simply going to be Y1 through Yn times Y1 through Yn, which is going to be Y1 squared, Y1, Y2, Y1, Yn, Y2, Y1, Y2 squared, and so on. So this is just simply, if I just write the outer product of a pattern with any pattern with itself, that's simply going to give you this matrix where every entry is the product of two terms. The diagonal entries are all guaranteed to be 1 because every y is either +1 or -1, and the diagonal entries are squared. So the weights matrix is in fact simply, if I use simple Hebbian learning, the weight matrix is simply the outer product of the pattern I want to store minus the identity matrix because you want the self weights to be 0. Right? Now, this is for a single stored pattern. If you want to store multiple patterns, then we saw that we would be using Hebbian learning, but you'd be summing the weights derived from each of the patterns that you wanted to store. So if I want to write it, so here the superscript P represents the specific pattern you want to store. Now, if maybe this is a better way of showing it. So what this means is that I'm summing over all of the patterns, the products of pairs of values. But this in turn means that remember that this guy is simply YY transpose minus I, just this one product, right? So this entire summation is the summation over all of the patterns that I would like to store, the outer product of the pattern with itself minus the identity matrix. And I can also write it differently. If I were to write all of my y's if I write a big matrix Y, which is Y1P, these are all the patterns, each of these is a vector. So this big Y is a matrix composed of all of the patterns I want to store. Then I can write W, then YY transpose is simply going to be summation P, summation over I, YIP, YIP transpose. This is just standard linear algebra, which means that the diagonal entries are going to be summed up. This is going to also add the diagonal entries for each of these patterns. So the simple Hebbian learning rule is going to give, for the simple Hebbian learning rule, you're going to have to subtract out the I, so that's just going to be YY transpose minus NP times I, because the diagonal entries occur for every single pattern. So you're going to have the diagonal term multiplied, factored in NP times, right? So this, again, everybody's clear about what I'm talking about over here. It gets thicker from here, right? So how many patterns can we store? We saw that you can store up to 0.14n patterns for large n. In reality, we saw over several examples that it seemed that we might actually be able to store much more than 0.14n patterns. So here is the claim that I stopped at. I claimed that I can always store up to n orthogonal patterns such that they are stationary. What I mean by that stationary is that if I set the network to this pattern, it's never going to change. And the question is why this would be the case. So we're going to start with this. We're going to look at the geometric interpretation of Hebbian learning and the network itself and try to make some sense of the whole process. So observe first that if I set the weights to be YY transpose minus NPI, then the energy of the network depends on this guy, right? So for any, if I'm trying to store any pattern any pattern Y, if I'm trying to store any pattern Y, for any pattern Y, the energy of Y is minus Y transpose WY, right, over 2. So, which means this is going to be Y transpose Y transpose minus NPI. Well, this is basically what I've got written on the slide, right? So if I expand this out, that simply I can pull this Y in here, and so that gives me this term, the first term, minus NP times. So what is the second term? The second term that's going to be, this is simply going to be Y transpose, this is a capital Y. These are all the patterns that I'm trying to store, right? Y minus, this is plus NP times Y transpose Y, because what he had in between was the identity matrix, right? And this term over here is simply going to be N, because each of these vectors is a vector of binary entries where all values are +1 or -1. So when I take this is simply the squared norm of the vector. Every component is either +1 or -1. So this is simply going to be the n, which is n is the number of bits in the vector. So the whole thing ends up being like so, right? But then observe that there's the difference between using this W as a weights matrix as opposed to using simply YY transpose without making the diagonal entry 0 as a matrix is just this. The difference in when I compute the energy assuming this to be the vector versus when I compute the energy assuming this guy to be the weights matrix, the difference is a constant, which is n times np. So which means that I don't necessarily have to make the diagonal entry 0 to understand the behavior of the network. As a where to understand the behavior of the network, I have to look at the energy as a function of the pattern, because having or not having the diagonal entries only adds a constant to the energy. So we're going to assume that the actual weights matrix is YY transpose. Now another thing I want you to observe is all of you are familiar with eigenanalysis, right? What is the, if I want to eigen decompose a matrix W, what would the eigen decomposition of W be? Anybody? Anyone? Guys, everyone's sleeping, right? So what is the eigen decomposition of a matrix W? So how did you define an eigenvector of a matrix? Anybody remember that?
Scalar times the vector equals the matrix times.
Yeah, guys, you're in a 700 class. You're supposed to be able to answer this question, correct? So I'm going to wait for you to answer this. Can you please repeat that? Right, this was your standard eigen decomposition, the definition of an eigenvector. And when you wanted to eigen decompose a matrix W, what was that? Anybody remember? This was E times lambda times E inverse, right? This was the standard eigen decomposition of any matrix. And so, or let me write this as Do we have the eraser here? Yeah. Let me write this as V just to match this guy, right? And specifically, if W was symmetric, then you got this behavior where the inverse of the eigenvector matrix was just the transpose of the eigenvector matrix, because all the eigenvectors are orthogonal to one another for a symmetric matrix, right? And alternately, anytime I got a matrix V such that V transpose V was I can compose W in this manner using any odd set of eigenvalues for the central diagonal matrix, and you're guaranteed that if I compose W like so, then this property is satisfied, right? Eigendecomposition either way, and it's very easy to show this, right? And we're going to be, you remember this stuff, don't you? Somewhere it's coming back. Okay, we're going to be using this a whole lot, okay? Now, the point is these two guys have the same eigenvectors. Why would I claim that? That's easy enough. I have, look at the first guy. So let V be an eigenvector, right? So y transpose minus n p I v equals y transpose v minus np v, right? So I can cancel this term out and you get y transpose. Basically, this shows that v is also an eigenvector of y transpose. So I can write, so this is, wait, this was, sorry, lambda, right? So S lambda. You're going to get the same lambda minus something. So basically what we are showing is that if V is an eigenvector of this first matrix, it's also an eigenvector of the second matrix. The only thing that happens is that the eigenvalues get scaled by n times np. I've been very sloppy over here, okay? So I'm going to use that. Also, this term y transpose is going to be a positive definite matrix. Now let's go back and look at this guy, right? I'm just adding this bias term for convenience sake. What kind of a function is this? It's a quadratic, right? It's a quadratic where the W matrix is positive definite. So if now it's how many minima will this function have? Anyone? Just one. It's a quadratic. It's a convex function because W is also positive definite, right? Or positive semi-definite. In this case, don't you find that there was something wrong with the statement I was speaking when I say that it's going to follow the energy contour and hit a local minimum? How many local minima will it have? It's a convex function, right? How many local minima does a convex function have? One. So why would I expect that this would actually store multiple memories? Anyone? Obviously, it has only one minimum. You'd expect any evolution to go to that single unique minimum. And yet I've been saying all along that I can store multiple memories. Why would that be the case? Keep in mind that W is positive semi-definite, E is convex, this is quadratic. So this is what the function is going to look like. It has a unique minimum, but then you have an additional constraint. So I'm showing you this figure from the top. If I slice it at different heights, each of the slices is going to be an ellipsoid because this is a quadratic function. But then you have this other constraint that the output of the network has to be binary. It can only be a +1 or -1. Every bit can be a +1 or a -1, which means that the values that the patterns that the networks can actually settle at are going to be on the corners of a hypercube, right? The network cannot evolve to this point. That's not a valid solution at all. The only valid patterns are the ones shown by the yellow dots. And over here, you will observe that these guys are closer to the center, so the energy at these 2 points is lower than the energy at these 2 points. So those 2 guys are going to be stored patterns. Those are low energy patterns. And if you start off at one of the other 2 corners, it's going to evolve to one of these corners, right? So observe that for every pattern, you have something that's diagonally opposite the center. That's going to have the same energy because it's a ball, right? Which means that if you don't have an external bias term, for every pattern you're going to have a ghost, which is the negation. On the other hand, if I have a bias term attached to each neuron, this is no longer required because things are going to shift, and the ghost of any pattern may not be a valid bit pattern at all. But if it's centered, then the negation of every pattern is also a stored pattern if you don't have a bias term. Everybody get that? Yes?
Just go back with this. I'm confused. Is this E term, is it concave or convex?
Pardon me? It is y transpose wy is always positive.
Minus half y transpose.
Yeah, so this is, well, it's
Is it concave?
concave. Well, it's got a ball. It has a minimum, unique minimum, right? So that's convex, right? Concave would be like so. It doesn't matter. It's terminology. You get the idea. It's a ball, right? So anyway, the point is it's a ball. Now, for any binary net, but then, what does it mean to actually perform this operation on top? This little, not this one, where's that? This guy. What does it mean to perform this operation on the left? So let's take a look. Let's actually draw the diagram. You know that every picture point must lie at the corners of the hypercube, right? So let's say this is your current vector. In this case, it's going to be 1, 1, right? What happens when I multiply y by w? What would happen to the vector? W is a square matrix. You're going to get a new vector, correct? Where would that vector lie? Somewhere. You can't really say, right? This vector may be after you multiply it. So these are the 4 valid positions that you're allowed to store the vector, that the network can store. When I perform a w times y, maybe it goes out here, right? It could go to a completely different location. And then when I take a sign, what am I really doing? I am pushing this down directly to the nearest corner and mapping it back to this, mapping it onto the nearest corner, right? So if a network is stable, if a pattern is stable, what does this mean about the pattern? Now keep in mind that all vectors in this corner are going to get mapped to, in this quarter of the plane, are going to get mapped to this point, right? Because this is the closest one. Everything in this quarter is going to get mapped over here. So any vector is going to get mapped onto the corner within the orthent that the vector lies in. So under what condition will a vector be stable? Stationary. It will be stationary if W transpose y, Wy is guaranteed to stay within the same orthent. If Wy stays within the same orthent, it's going to get mapped back onto itself. Otherwise, it's going to get mapped to a different pattern, right? So basically, what's happening is that anytime you take a vector y and you multiply it with w, it becomes some other vector. When you take the sign, you're projecting it down onto the closest corner, and A vector is stable if sine of y, wyp is stationary if sine of wyp equals yp, right? And so for all target patterns, you want this pattern to hold, right? Now, so which means that if I want this pattern to hold, if I want to store these patterns geometrically, I want to design my y, my w, such that when I multiply the y vector with w, the result stays within the same orthent as the original y itself, right? So what is the simplest solution of this kind? If y is simply an eigenvector of w. That way you are guaranteed that, so if y is an eigenvector of w, what would happen over here? If I take this y and multiply it with w, where will the resultant vector be? Same line, right? It's going to come back onto itself. And therefore, you're guaranteed that it's actually stored, because it keeps getting mapped onto itself, correct? And so one way to ensure that a pattern is stored is to make it an eigenvector of w. Now let's go back to this other little guy over here. Actually, how many such y's can we have? How many eigenvectors can the W matrix have? N. So you can store at most n patterns guaranteed, right? With any kind of guarantee, right? So only n patterns. You can store at most. It doesn't mean that you will always store only n patterns. It means that you can store n patterns on purpose, but other rubbish can happen, as you can see. How many? Now consider orthogonal patterns. How many orthogonal patterns can we have? If I have an n-bit string, how many patterns can I compose of n bits such that they all differ in exactly n minus 2 bits? Anybody? How many can I compose? If an n-bit pattern differs from other bits in n minus 2 bits, can you just flip your phone over? No, okay. Okay. So if an n-bit pattern can actually differ from if an n-bit pattern differs from another pattern in n minus 2 bits, the two are orthogonal. They're at 90 degrees to one another. If I have n-bit patterns, it lives in an n-dimensional space. How many vectors can I draw that are all orthogonal to one another? N, right? So which means that you can store you can have at most n strings, bit strings, which all differ from one another in exactly n minus 2 bits. You can't have more than n, right? Very simple arithmetic, nothing fancy. Second, we also saw that the eigenvectors of our symmetric W matrix are going to be orthogonal to one another, right? The eigenvalues may be either positive or negative. So, given all of these patterns, if I want to design a matrix W such that sine of wyp is the same as yp, then what is the largest number of patterns we can store? As many as the number of eigenvectors, no more than n. And let's assume that I can design my W such that these guys are the eigenvectors of W. And I'm assuming that these are all orthogonal patterns for now, okay? So if I have orthogonal patterns, I can just create my Y like so. I define my W in this manner. And then I'm going to set the lambdas all to be identity, so that they are, because basically I want the vector to map onto itself. The lambdas, the eigenvalues don't have to be identity, they only need to be positive. I don't want the pattern to be flipped and go off into the wrong orthent, right? So in this case, then these patterns are all provably stationary. So I can, if I have n orthogonal patterns, I can actually provably construct a Hopfield net for which all n orthogonal patterns are stationary. If I have k patterns, k less than n patterns, and they are all orthogonal, then I can fill in a bunch of the remaining orthogonal patterns somehow and set their corresponding eigenvalues to 0, and I can still compose my eigenvector matrix, my Hopfield network, the weights matrix for my Hopfield network, such that my k patterns are all stationary. Right? Everybody see what I'm talking about, right? So here, what is the problem with simply composing a network in this manner? This is just simple Hebbian learning. And here's the problem you're going to find. So observe that if I have n orthogonal patterns, assume that I have n orthogonal patterns. How much of the space do n orthogonal patterns actually span? All n dimensions. If I have n bases, I can get to any point in my space using n vectors, correct? And they all have eigenvalues 1 using this little composition. So now, because the n vectors span the space, I can represent any vector y as a linear combination of these guys, right? So that means regardless of the current configuration of the network, I can express the current configuration of the network as a linear combination of my stored patterns. What happens as far as the evolution of the network is concerned? W times y is simply going to be a1 times wy1 plus a2 times wy2 and so on, right? But then we know that these guys, these patterns which I've stored, are my eigenvectors. When I multiply them by w, they do not change. As a result, this is simply going to give you right back, give you a1 y1, a2 y2, a and y, and right back, which is going to give you y. Every single pattern is stable, right? So this is stationary, which means that if I just take n orthogonal patterns and use simple Hebbian learning, where every pattern is represented exactly once, and compose my weights matrix, it means not only those n patterns, but pretty much any other pattern that you can represent for n bits is going to be completely stationary. Is this memory? This is rubbish, right? So basically, this means that it's a completely useless network, right? Although these patterns are all as far apart as possible from one another, trying to store them all gives you a completely useless network. What happens if I'm trying to store less than n patterns? If I'm trying to store less than n patterns, let's say I'm only trying to store k patterns, right? Then my weights matrix includes a bunch of other eigenvectors that I don't care about. But then if I have any pattern, now if I'm using Hebbian learning, for these k patterns, the eigenvalues are all 1. That's the way you define it, right? Every pattern is included once in my Y matrix out here. The way we wrote it, every pattern is represented once over here, right? So all of them have eigenvalue 1. And so this means now if I have any pattern Y, which is a linear combination of the k orthogonal patterns that I have stored, meaning it lives in the subspace represented by these k patterns, then multiplying that matrix by y is going, that vector by w is going to return the vector itself. So basically, so what we are saying is that if I have in 3 dimensions, let's say, if I'm only trying to store these guys, say these 2 guys. So I'm not using the 3rd dimension at all. I'm only storing 2 patterns, which means that 2 patterns are going to span a 2-dimensional subspace. Then if I take any other vector y in this plane, that vector y, when multiplied by w, is not going to change. Why? Because this vector can be written as some a times this guy plus b times this guy, and these have eigenvalues 1. So w times y is going to is just going to return itself. So what this means is that if I'm trying to store k orthogonal patterns, any other bit pattern which lies in the subspace spanned by those k patterns is also stable. The network remains useless in the space of the patterns that you're trying to store. So this tells us something really contradictory, that if you have patterns that are as far apart as possible, it's really, really hard to store them if you're using Hebbian learning because of this strange behavior, right? So everybody get up what I'm saying, right? So how do you fix this? Why is this reason? Why is this happening? This happens because all of our eigenvalues are 1. So for example, if I were trying to, if this vector This happens because I can write any y equals a1 y1 plus a2 y2, and wy equals a1 lambda 1 y1 plus a2 lambda 2 y2. And because these eigenvalues are 1, the vector returns to itself and it becomes stable. What would happen if these eigenvalues were not 1? If one of them was greater than the other? If one of them was greater than the other, then the vector is going to change its direction. And when it changes its direction, now it can become unstable. Because now when you take a sign, it can end up going somewhere else. Right? So what this really means, but then, what does it mean to have eigenvalues not equal to 1 when you're trying to store these patterns? It's like saying that if I have an eigenvalue of 1, when I'm trying to store these patterns using Hebbian learning, basically I'm just taking y transpose. I'm taking the summation of the outer products of all of these guys. The eigenvalue is the number of times the pattern occurs over here, right? So if I repeat any pattern, it's going to have a greater contribution to the weights matrix. It's like saying that pattern has a greater eigenvalue. But then you're also saying that pattern needs to be memorized more than the other patterns. So the moment you make the patterns asymmetric, unequal in their importance, then magic things can begin to happen. So here are the two questions. What happens when the patterns are not orthogonal? We've been speaking of orthogonal patterns. What happens when the patterns are presented more than once? Different patterns are presented different numbers of times. It's like it's equivalent to having unequal eigenvalues. Then, if I give you some other collection of, if my patterns are not orthogonal, and I'm allowed to represent some pattern more times than others, then can I predict the evolution of y? It turns out I can still predict the evolution of y, exactly how it will change, by simply analyzing my weights matrix. But then, more important than that, it's how do I turn this off? Turn off. Some of these people get very, it's a spam call. Some guy calling from India telling me he wants my social security number. Because you see my taxes are all not paid and it's very important for them to say rescue my credit card. Anyway, so so let's look at what happens in this case. I can try to, suppose I gave you these y's which were not symmetric, they were not orthogonal, and I had different numbers of y's, repetitions of different y's. How would I analyze the behavior of the network? I can still analyze the behavior of the network. I can go ahead and find the eigenvectors of W. Then I can represent every vector y as a linear combination of my eigenvectors. And then I can find out what happens when I repeatedly multiply that y by W by the weights matrix, which means that the different so let me write this down. For a generic vector, I can write y equals a1 v1 plus a2 v2 and so on, where v is the eigenvectors of W. I can write this for pretty much any vector v, right? So then I can just write that W times y equals a1 lambda 1 u1 plus a2 lambda 2 u2 and so on, right? And what is W raised to n times y? That's going to be a1 lambda 1 u1 plus a2 lambda 2 raised to n u2. and so on. Right? Every time I multiply by W, each of the individual eigenvectors, the contribution of each of the individual vectors is going to get stretched by lambda. Eventually, if I keep repeating this process, what will happen? The whole thing is going to explode in one direction, the guy which has the largest lambda. The others are going to collapse, right? And you're going to end up pointing in the direction of the largest lambda. Except now you have, so this is not good behavior. But then what really happens is that we are not really doing Wy, we are doing sine of Wy, correct? And so what will happen, so this is still going to collapse in the direction of some of these eigenvectors. After each, each pattern is going to basically collapse onto the closest eigenvector, or to the signed version of the closest eigenvector. And this is something that you can actually use to construct your W's, right? Your weights matrix. So here's the bottom line. With a network of n units, the maximum number of stationary patterns is actually exponential in n. It's not n. We saw this in the case of where all of my target patterns were orthogonal. Every pattern was stored. Every pattern was stationary, right? We had 2 raised to n patterns that were stationary. It doesn't mean that you want all 2 raised to n patterns. It just meant that when you tried to store n patterns, you got a whole bunch more other patterns that were stationary. So for a specific set of k patterns, if you give me k patterns, I can always compose a network such that all k patterns are stable, provided k is less than or equal to n. This is a guarantee, right? It doesn't mean that only those k patterns are stable. You can end up with many parasitic memories, other stuff that you don't really want to remember, completely fake stuff, right? So everybody with me so far, right? So we're going to switch from this whole, what I want is to find a network which can store any specific target of k patterns, which don't necessarily have to be orthogonal. Remember that it depends on, the behavior of the network depends on the eigenvectors, but the eigenvectors are not predictable from the y's if the y's are not orthogonal to one another. So you need to figure out what the weights matrix is. But then I want a second characteristic. I don't want to have too many parasitic memories. I want to store those k patterns. I do not want to store other patterns, meaning I want those k patterns to be energy wells, but I don't want other energy wells, right? So how would I do this? We'll pick it up, but a quick summary of everything we've covered so far. Hopfield nets with n neurons can store up to 0.14 n patterns through Hebbian learning with a 99.6% probability of recall. And Hebbian patterns law assumes all patterns are equally important. For orthogonal patterns, these are the eigenvectors of the constructed weights matrix where all eigenvalues are identical. This is what Hebbian learning gives you. And in theory, the number of stationary states can be exponential in n. The number of intentionally stored patterns, stationary and stable, can be as large as n, right? You get a bunch of unintentionally stored patterns, comes with parasitic memory. So let's try to see how we know this can be done, so the theory says. Let's go and see how we can actually compose a weights matrix without using Hebbian learning. Hebbian learning kind of works, but it fails, as we saw. It's not completely predictable behavior, and sometimes if your patterns are orthogonal to one another, you can actually get rubbish, for instance, right? So can we use a different tack? And to do this, we're going to use an optimization framework. First, let's go back and try to start with the objective that the network implicitly tries to minimize when it evolves. You initialize the network with some pattern, and it begins evolving, and it tries to minimize this energy E, right? So you want this energy E to be a local minimum for all the target patterns that you're trying to store. At the same time, for other patterns, you want this energy to not be a local minimum. You want this to be high because you want the network to begin evolving towards the patterns that you're trying to store, right? So I want to estimate my weights matrix W and this bias B. I've reintroduced the bias such that the energy is minimized for my target patterns. It's maximized for all other Y, Okay. Now, it's unrealistic to expect to store more than n patterns, but we can make those n patterns memorable in the sense that they are actual energy wells. This is what we want to do. So first, I'm not going to explicitly represent the bias. The bias is like having a fixed value, one bit that's always fixed to 1. And so you can define the energy of the network as we always did. You want to find the weights matrix such that the total energy of all the target patterns is minimized. But what would be the problem with just building a weights matrix in this manner, trying to minimize the total energy of all the target patterns? Anyone? What would be the problem with this? One of you guys, come on, wake up. So what would be the problem? Yes. Someone else? William? No? It's too early in the morning for you to figure this out. We are not saying anything about the non-target patterns. So in the process of minimizing the energy of the target patterns, you could be minimizing the energy of the non-target patterns as well, right? So what you really want to do is to minimize the energy of the non-target patterns, but you want target patterns, but you want to maximize the energy of the non-target patterns, right? So basically, here is the actual objective we want to do. You find the W weights matrix such that the energy of the target patterns is minimized, the energy of the non-target patterns is maximized. I can use simple gradient descent for this. This is the derivative of this objective function, which is the sum of the outer products of all of the target patterns minus the sum of the outer products of all of the non-target patterns. So you're going to keep updating your weights matrix according to this gradient. Very simple, right? So what exactly does this mean? What is this first term? This first term is emphasizing the contribution of the target patterns. You're trying to minimize this guy, right? Minimize the energy at all of these guys. And you can emphasize some patterns more than other patterns by repeating those guys. So if I say that I want to store this image and this image, but it's much more important for me to recall that image than this guy, then you would present this one 5 times, and the other pattern that's not as important maybe only twice, right? So by repeating the different patterns that you're trying to store different numbers of times, you're assigning importance to these patterns. So more repetitions is greater emphasis. These guys are all the other patterns that you don't want to store. And how many of these will we have? It's exponential in n, right? So that summation is going to be over an exponential number of terms. So clearly, this is an infeasible optimization problem, right? So now, look at what we are saying. Here's what the energy contour is going to be. In fact, this energy contour is going to be kind of quadratic because as we saw, the energy is quadratic. But so let's say I have some current setting of W. If I have some current setting of W, then, and say these are my target patterns, then this is the energy assigned to the target patterns by the current setting of W. When I modify my W using my gradient descent, I'm trying to change the W such that these values get pulled down. And the second term is trying to increase the energy of the other guys. It's trying to pull up the W everywhere else, right? The problem is you're trying to raise everything and you have an exponential number of such points. Do we really need to pull up everything? Not really, right? Think of it this way. If in the current setting of W, this guy is a pattern, and there's a valley downstream of it, I only need to be pulling up the valleys. I don't need to pull up every pattern. If I just pull up the valleys, that should be sufficient to pull up all of the network, except at the target, or the energy of the network everywhere except at the target patterns, right? So given this, first, how do you identify the valleys? If I were to ask you to identify the energy valley, how would you do this? Just run the network and see where it evolves to, right? So I can just initialize the network randomly, let it evolve. Wherever it settles, it's going to be a valley. So this gives me this simple update rule. Compute the total outer product of all of the target patterns, where you represent more important patterns more frequently. You randomly initialize the network several times and let it evolve and settle at a valley, and compute the total outer product of all of the valley patterns, where these valley patterns should not be target patterns. If a valley pattern is a target pattern, you let it be, right? And then you update the weights like so. Or you can do the stochastic gradient descent version, where you randomly select a target pattern, where the sampling frequency of a target pattern must be dependent on the importance you're assigning to the target pattern. More important patterns are going to be sampled more frequently. And then you randomly initialize the network, let it evolve, settle at a valley, and you're just going to use the standard gradient descent, stochastic gradient descent update rule, right? So nothing fancy. We haven't done anything complicated. But then, do you need to randomly initialize the network each time, right? Random initialization is not the best thing to do. Look at this guy. If I'm trying to recall these three patterns, does it matter if I pull up this valley? It doesn't. The valleys that really matter are the guys that are next to the patterns that I'm trying to store. I want those guys pulled up so that the patterns I'm trying to store become valleys, right? So if this is the case, then what do I want to do? What is the natural correction of my algorithm? Start from a target point, right? So what I will do is I will not care about these guys. Spurious valleys are in the neighborhood of my target patterns are more important. So I'm going to initialize the network at valid memories and let it evolve, and it will settle in a target it will settle in a valley. And if the valley is not the target pattern itself, then I'm going to raise it, right? Yes?
So wouldn't the call site for the second valley, wouldn't like other points would sort of
So the point is it's too far away from anything you're trying to remember, right? So it doesn't really matter. The point is we're trying to focus on, so the entire point is, since you're thinking of this as content addressable memory, if something that's very far away from anything you're trying to recall, you don't really care about that.
Yeah, but wouldn't that sort of become a non-desirable target pattern?
It's a parasitic pattern. But then if you focus on the target patterns over here, yes, you are going to get parasitic patterns.
Okay.
But
so in the end it will go away.
It will not go away. The whole point is that they're just going to be an exponential number of these guys.
Oh, I see.
So you don't really want to be wasting a lot of effort on those, right? That's the whole problem, right? So the idea is that if you focus on the stuff that you do want to remember, hopefully you get a far fewer of the other guys, but there are no guarantees. And this still doesn't solve the problem, right? So here's the algorithm we're going to be. Compute the total outer product of all of the target patterns, where more important patterns are represented more frequently. Initialize the network with each target pattern and let it evolve, and then use the outer product of the target patterns at the valleys to pull them up. And this is the SGD version. Same thing, right? Sample a target pattern to compute this term, then initialize the network at that YP and let it evolve, and you're going to update the weights. Again, nothing fancy. We'll just go, but then I'm going to take this one step further, right? If I'm performing the SGD, for instance, and let's say I have two patterns of this kind, and this guy happens to be at the valley for this one, then what happens? If I start from this point and let it evolve to the valley, and I pull it up, I'm erasing a stored pattern, right? So how would you fix this? You have no way of knowing whether you're in the middle or not, but what you can say is that you can say, I want the memory to be at least 5 bits from my target pattern, right? And so, instead of letting it evolve till it hits a valley, you can just say, you see that there's really no need to raise the entire surface or even in every valley. It's sufficient to raise the neighborhood of each target memory. Sufficient to make the memory a valley. And the broader the neighborhood considered, the broader the valley, right? So what you're really going to do is, you're not going to evolve all the way down. Maybe you evolve 3 steps and then pull that up. And if you pull it up, the other guy remains a valley, right? So it avoids the problem of down valley targets. So if you were doing the SGD version, you'd sample a target pattern, compute the outer product, then let the network evolve. Let the network evolve for 1 or 2 or 3 or 4 steps, and then get a down valley position, and then you update the weights. Right? Yeah.
Won't this result in an energy field that has, like, not every target pattern has the same size neighborhood? I mean, isn't this going to result in, like, some of them are going to, like, if you put a bunch of values in, it's going to descend to a target, but others you have to put a very tight radius around?
That's it, because it depends on the neighbor, how close the target or far. It depends on multiple factors. How close or far apart the target patterns are,
Yeah.
and how frequently you present any target pattern as a measure of its importance, right? So yes, it's not going to be an even field, but this is governed not just by the algorithm itself, but also by the patterns you're trying to store and their relative importances, right? Okay, so here's a summary. In theory, the number of intentionally stored patterns can be as large as n. Networks that store n memories can be trained through optimization. This whole thing was an optimization algorithm, right? And by minimizing the energy of the target patterns while increasing the energy of the neighboring patterns. Everybody with me so far? What we've shown here is that the memory capacity of an n-bit network is at most n. You can try to store more than n patterns, but there are no guarantees. The only thing I can guarantee is that if you try to store up to n patterns, it is possible for me to find a weights matrix which will remember those n patterns, right? So now, if I want to store more than n patterns, I absolutely insist, I want to store more than n patterns. This is an n-bit patterns, right? My patterns, again, the number of patterns I can store depends on the number of bits on the pattern, the way we've defined this, right? But I want to store more patterns than the number of bits. What would the obvious next step be? Anyone? So here's where a little bit of orthogonal thinking comes in. Right until here, we were with John Hopfield. And then we switch into Mr. Hinton, right? And I can append a bunch of k bits to the pattern that I'm trying to store. I don't care what those k bits are. And now I have n plus k bits, right? And now my network is going to be not a network of n units, it's going to be a network of n plus k units. Of these n plus k units, I'm only interested in n bits. I don't care what the remaining k bits are. But with a network of this kind, how many patterns can I store? N plus k, right? So just by adding a bunch of don't care bits, I can suddenly increase the capacity of my network. So you add a large number of neurons whose values, actual values, you don't care about, right? So the new capacity is n plus k. And although you're only interested in the first n neurons, you're still only interested in n-bit patterns. But you want to store more than n-bit patterns. So you add a bunch of don't care bits, right? So you're going to call these guys the visible neurons and these guys the hidden neurons. There's no reason to be calling them hidden. We're calling them hidden. You should be calling them don't care neurons, really, right? And the visible guys are the bits who you want to see, and the rest of the stuff you don't really care about. Okay? But once you begin adding these extra things, questions come up. If I want to store a specific pattern here, what must the values of these neurons be? How should I set them, right? And how should I set them is not very clear immediately. They can be set to anything. So basically, if I think of it in terms of bits view, I have n bits, and I'm trying to store more than n-bit patterns. So I'm going to be appending a bunch of so-called k hidden bits, whose values I don't care about. I'm going to pad these patterns with k don't care bits, so the new width of the patterns is n plus k. So we can store n plus k patterns, but then we don't really care what these values are. This is a pattern you want to store. You don't care what these values are. What values would you fill them in? Simple option, you can fill them in randomly, flip a coin at each bit and fill them in randomly, right? The problem with filling them in randomly is they're very likely to end up being orthogonal. And we know that we don't really like orthogonal patterns because they have they make everything possible, right? But then here's the other thing. If I have a single visible pattern, I can create multiple extended patterns with the same single visible pattern. So my ability to increase the width of my bowl has suddenly increased, because I can say that, although I have this one visible pattern, I can append k bits in 50 different ways and make 50 copies of this guy. And I've increased the importance of this one guy by a factor of 50. And I can increase effectively the size of the bowl, energy bowl, which will collapse to that pattern. And the point is, it's going to collapse to 50 different points, right? But in each of the cases, the visible bits are all going to be the same. So I've actually increased my network. Now, given that we've figured out how we actually fill in these gray bits, how do you actually store the patterns? We can just go use the same optimization method that we just saw, and it should just work, right? So, and how do you retrieve a memory? Same thing, the usual evolution mechanism. But the problem over here is that when I use the usual evolution mechanism, I'm not taking advantage of a key feature of the extended patterns, which is that making errors in these bits doesn't matter, right? So long as I recall the first n bits correctly, I don't care if I've made errors in the other bits. This is a feature that I can actually use to my advantage, right? And so by adding these k extra bits, I'm getting both extended storage and additional robustness. So the value taken by these k hidden neurons during recall doesn't really matter, even if it doesn't match what we tried to store. So how do we take advantage of this? Now, so here's the situation. Simple random setting of the don't care bits and using the usual training and recall strategies of Hopfield networks should work, but it's not a great idea, particularly because it doesn't exploit the redundancy of the don't care bits. And to exploit this properly, now you have to take a slightly different perspective. You have to view the Hopfield network as a probabilistic machine. I mean, you can do it without viewing it as a probabilistic machine, but when you think of it as a probabilistic machine, the math becomes simpler. So for this, I'm going to go back, and I'm going to go back to spin glasses. For binary y bit patterns, the energy of a pattern is the analog of the negative log likelihood of a probability distribution called the Boltzmann distribution. Minimizing the energy maximizes this log likelihood. So this is the energy, right? This is how we defined it. Let me define a probability distribution which is e raised to this negative of the energy, right? What does minimizing the energy do? It's the same, since the energy is the log of the probability, minimizing the energy is the same as the maximizing the log probability, which is the same as maximizing the probability, right? And so this seems like playing tricks. I just took a number, exponentiated it, called it a probability, and then I'm playing with it, right? So what is the point of doing all of this? It turns out there's actually a nice physical interpretation to this, and it's not being pulled out of thin air. And for that, let's go back and look at the physical system. So I can define for the dielectric material that we were speaking of, the spin glass, the energy of the current configuration, remember? Which was e raised to minus half y transpose wy minus b transpose y. We saw this. So we've seen this a few times. So it turns out that if I think of this system as being at some energy, at some temperature T, then how the system actually behaves, if you go down to physics, is that all of the dielectrics don't stay stable. They don't just stay at one position. They're constantly changing. They're constantly flipping around. So what happens is that if you take a snapshot of the dielectric at any time, and you look at the configuration of the dipoles, and then if you take a snapshot of the material at a different time, and you look at the configuration of the dipoles, they may be entirely different. But the probability of finding it in any specific configuration y is proportional to e raised to minus the energy of y. It specifically is proportional to e raised to minus energy of y divided by kt, where k is the Boltzmann constant and T is the temperature. Now see the observed thing. When the temperature is very high, all of these probabilities are low, which means that the system is continuously changing its state. You can't identify a unique any state which has a very high probability. On the other hand, if the temperature is 0, then the system is going to be in the state with the lowest possible energy, with a probability of 1, right? And the whole thing. So for our system, for this guy, this is basically like the Boltzmann distribution with a temperature equal to 1, right? So continuing with the Boltzmann analogy, what is really happening is that this system probabilistically selects states with lower energy, meaning if the material is set at some energy in some configuration, then it's going to randomly keep changing its state, but it's always going to favor states with lower energy, and you're less likely to find it at any time in a state with higher energy. This is just the physical property of the system, right? So, and if the system cools, so the temperature keeps going down to 0 very, very slowly, this is the process of annealing, which is used to temper steel and glass and all of these other materials, then eventually it's going to arrive in the lowest energy state, which has the most stable configuration. And it's actually very easy to show that this has got to be the probability distribution. We will see this in a few minutes. So selecting, in our case, if I initialize the system with any configuration, I can think of this as an even closer analogy of the spin glass, and say, instead of saying that the system must deterministically evolve towards lower energies, I can say the system must stochastically evolve towards lower energies, which is to say that you draw a sample from the Boltzmann distribution with time t equals 1 in a universe where the Boltzmann constant is 1, and with high probability that it's going to evolve to a state with lower energy, but with some low probability it may actually increase its current energy, right? So in this case, now let's go back and to see where this interpretation comes from. Look at this guy. If I define my energy this way, this was the objective that we were minimizing, right? You were minimizing the total energy of the target patterns. You were maximizing the total energy of the non-target patterns. But this guy, so if you look at the gradient, it was W plus, the gradient was a sum of the outer products of all of the target patterns, but then each target pattern had a corresponding weight associated with it, which was the number of times it was repeated. It was the importance you assigned to it. So also, each non-target pattern had a weight associated with it, which was how much you really didn't want it, meaning we ignored target patterns we ignored noise patterns which were very far from any of the targets, and we assigned greater importance to the guys that were close to the target. And because you're sampling the more important target patterns more frequently, the guys in the vicinity of the important target patterns are going to be more represented, right? So overall, these guys actually look like expectations. You can think of this as the expectation of the outer product computed over a probability distribution for target patterns, where the importance of the target pattern is given by this probability distribution yp, right? And you can think of this guy as an expectation, again, this is just a weighted combination of outer products, right? It's an expectation of an outer product, where the expectation is taken over a probability distribution, where this term now actually also depends on the current value of W, because the current value of W decides which noise patterns are close to my target and which ones are not, right? And so overall, the behavior of the Hopfield net, even the training process, is analogous to annealed dynamics of a spin glass characterized by a Boltzmann distribution. Let's just spend 5 minutes at this before I close. Let's explicitly model the Hopfield network as a distribution. Now, revisiting this thermodynamic phenomenon, is the system actually in any specific state at any time? Not really. The system is continuously evolving. You set it in some state, and because of the temperature, it's always changing, but it's more likely to go into a lower energy state than into a higher energy state, right? So what you're really characterizing, what the energy is really characterizing is the probability of the state. It's also characterizing the expected value of the state. So how do the thermodynamics actually work out? A thermodynamic system at temperature T can exist in one of many states, potentially infinite states. If you have n dipoles, there are 2 raised to n possible states that it can actually live in. At any time, the probability of finding the state in some state S is given by Pt of S, which is the probability, which is a function of T. I haven't told you what Pt of S is. I'm saying that there is some probability of this kind. At each state, it has a potential energy Es. This is what we saw, right? But then, so the internal energy of the system, representing its capacity to do work, is basically the expected value of the potential energy of the system. Over here, meaning you're summing over all of the states, Pt of S times EFs. This is the capacity of the system to do work. But then there's something else which is interfering, which is the disorder, the entropy in the system. When the system is has high temperature, it's sort of bouncing around. It likes to behave randomly, and because it likes to behave randomly, the randomness in the system keeps it from being controllable, right? And so that is the entropy of the system. And so the entropy of the system is simply given by exactly a conventional formula for entropy. In fact, the whole definition, the concept of entropy in communication theory and machine learning came from thermodynamics. This was due to Rayleigh, I think. Which is minus P of S log P of S. You remember this guy, right? So you have these two things, sort of facing off. The potential energy of the system, which is the capacity of the system to do work, minus the disorder in the system, which is the entropy of the system, and the balancing factor is this K times T. The greater the time temperature T, the more disorder in the system there is, and the less net capacity the system has to do work, because the system is disordered, right? So what will happen? If I set the system at some fixed temperature T, it's going to sort of work its way down such that it keeps revisiting the states. It's going to keep bouncing around between the various states until it arrives at a probability distribution over states which has the minimum free energy for the system at that state. So this is the free energy of the system, this whole thing, which is potential energy minus the disorder, right? And it's going to keep bouncing around. So if I raise the temperature of a system, it's going to keep evolving until eventually it arrives at a stationary probability distribution over all states. And that stationary probability distribution over all states is the distribution that minimizes this term over here. And this distribution is known as the Boltzmann distribution after the guy who discovered it. And in fact, if you minimize this with respect to Pt of S, it's a two-step derivation, which will just give you that the probability for any state S is given by e raised to minus E of S divided by Kt. So if you ever wondered where the Boltzmann distribution came from, basically it's just a very simple, it's not a very complex arithmetic equation. All of it is something that you can do without having to invoke fancy math, which is that it just tries to minimize the free energy of the system at any given temperature, right? Note the dependence on T. At temperature T equals 0, the system will always remain at the lowest energy configuration with probability 1. It's beautiful, right? It just falls out. And so this is what I can actually use when I define the energy of my nest system. I can define that of my Hopfield network. I can define the energy of the system. I'm assuming that the temperature T is 1 and the Boltzmann constant is also equal to 1. And if I did that, then if I thought of this whole thing as a stochastic system where the state keeps changing, then the probability of finding the system in any given state is going to be given exactly by the Boltzmann distribution, right? This is the probability of different states that the network will wander over at equilibrium when it has finally arrived at equilibrium. It continues to evolve, and then if you keep drawing states according to this distribution, eventually, if you let the system evolve, if you just start this Hopfield network and you let the system evolve, then how exactly will it evolve? We'll look at this in the next class. Eventually, it's going to arrive at this distribution. So this is simply adding a little, because we started off by building on the notion of a spin glass. We're just continuing the analogy one step further and converting this Hopfield network into a stochastic system, but with a very specific purpose in mind. We want to enhance the ability of the system to store patterns, but in the process, you also end up with a network that actually represents a probability distribution. We'll continue with this in the next class. Any questions? Anyone Piazza questions? No? Thank you.